Good morning to all. Today we are going to discuss about Orgel diagrams. It is an important topic in the field of inorganic spectroscopy. The electronic spectrum, that is the color of transition metal ion in complexes, refers to the absorption of light in the region of UV visible from the electromagnetic spectrum, and the interpretation of UV visible spectra will give some useful information about the energy levels present in the transition metal ions. Usually, the UV visible spectrum recorded under the 200 nanometer to 800 nanometer, and in terms of wave number, it is 12,500 centimeter inverse to 50,000 centimeter inverse. 50,000 centimeter inverse. In a multi-electron system, many energy levels are exist which is not seen in a single electron system, and we know that the concept of spin angular momentum and orbital angular momentum not hold good for an entire multi-electron system in which these two values interact together or couple together to give a resultant angular momentum denoted by capital letter El, and the total energy and total angular momentum for an entire multi-electron system can be denoted by term symbol which is 2s plus 1 L J. J is a new quantum number combination of L plus S and L minus S. For more than half-filled orbitals, we are taken N plus S value. For less than half-filled orbitals, we are taken minimum J value, that is L minus S value. In the table, we can see that for 0 and total angular momentum, we get S term. For 1, it is P. For 2, it is D, and so on. In order to understand the electronic transition in metal complexes, we must have some idea about the splitting of Russell-Sanders state or the term in octahedral and tetrahedral fields. From the table, we can see that the S term is split into, or not splitting, it is transferred to A1G set. That means that the S orbital is spherical when the ligand field approaches the central metal. The S term not experiencing any ligand field, so it is singly degenerate, represented by A symbol. In the case of p orbital, there is three p orbitals are there: px, py, and pz. These three are directional. When the ligand is approaches, these three experience equal ligand field strength, so the energy remains the same, so it is triply degenerate. In the case of D, there are two type of orbitals in between the axis and along the axis, so it is split into e.g. doubly degenerate set and a triply degenerate set. 2 plus 3 is equal to 5. In the case of 7f orbitals, 3 triply degenerate and again a T1G. That means the difference is in the plane of symmetry. T1G and T2G. The G represent the center of symmetry, and an A1, A2G, it is a singly degenerate. In the case of G, it is split into 4 and so on. And we are having two selection rules are there. First one is spin selection rule. The rule says that the electronic transitions having the no change in spin, the quantum number is spin allowed transition. The spin allowed transition is delta S. Spin allowed transition delta S is equal to 0. We are having an example for D7 system. We are having D7 system having 3, 4 and 5, 6 and 7. Here when the D7 electron, that is the cobalt 2 plus electron having some amount of energy in the UV visible region, and the electron promoted into an excited state, that is 1, 2, 3, 4, 5, 6, and the last electron is promoted into an excited state and goes into anti-parallel state. Here we can see that we are having three unpaired electrons, 1, 2 and 3. So the total spin is equal to 3 by 2. Here also we are having the 3 unpaired electron. The total spin is equal to 3 by 2. So the electronic transition taken place with no change in the spin. This type of transition is spin allowed transition, where in the case of D5 system, 1, 2, 3, 4 and 5, 5 electrons are there. D5 system absorbs energy and the electron promoted into one electron in the ground state promoted into an excited state. When the electron get excited, it is anti-parallel to the Eg energy level, and while considering the spin state, here is 5 by 2. Here we are having only 3 unpaired electron. The total spin is 3 by 2. It is spin forbidden. The second selection rule is Laporte selection rule, that is the delta L not equal to 0 in a transition. It is Laporte allowed transition. Or precisely we can say that the delta L must be plus or minus on range. That is, the transition from s orbital to p orbital is Laporte allowed. From p to d it is Laporte allowed, and d to f is Laporte allowed. But the transition from s to p is Laporte forbidden, and p to f also Laporte forbidden. Here the delta L value is equal to 2, and also the transition from s to s, that is the delta L value is equal to 0 also, and P to P and D to D and F to F is Laporte forbidden. So we know that the DD transition is responsible for the color of transition metal ions. We in manganese having the D5, the D5 system also having a D5 system. D5 system is spin forbidden. It is pale pink because here DD transition is not possible, but here the pale pink because of the vibronic coupling or the distortion of symmetry or the mixing of energy levels, that is D and P orbitals in the transition metal ions. Here the Orgel diagrams have important diagram for representing the energy levels, and we can understand the electronic spectral transition optical. Also we can obtain some magnetic property of the transition metal ions. These are the correlation diagrams represents the electronic terms in reference to their relative energies. The relative energies is in the y-axis. The x-axis we are representing the ligand field strength. Here is a vertical line represents zero ligand field. Zero ligand field means that it is a free ion time. Free ion time is represented in the middle of the vertical line. It is introduced by Leslie Orgel, and it is applicable for only high spin tetrahedral and high spin octahedral complexes. The first diagram for D1 octahedral complex, the typical example is titanium complex, that is the hexa-aqua titanium 3 plus complex, titanium 3 plus state. It is in D1 electronic configuration. D1 electronic means here we are having 1, 2, 3, 4. D1 electron is 0, minus 1, minus 2. So the total angular momentum, that is the modulus of L, we get 2. It is denoted by the symbol 2D. For a free electron, free metal ion, it is the term symbol is 2D. That is the spin multiplicity is equal to 2 because there is only one electron is present. When the ligand field strength is increases, that is the 6 aqueous ligand means the water molecules approaches the central metal ion, the energy level split into two, T2G and EG. There is a promotion of one electron from the T2G energy level to the highest energy level EG, and we get only one transition, that is from T2G to EG, that falls in the range 20,300 centimeter inverse. That means that it absorbs energy in the region of green and yellow and transmit energy in the region of red and blue. So it looks like as purple. Titanium, hexa aqua titanium complex having a purple color. Here we can understand the number of unpaired electrons, ground state times and number of DD bands. Here for titanium complex having one DD band is there. For D9 system, the difference is here in D9 system, copper 2 plus having the D9 system. In D1 state, we are having only one electron. Here we are having 3, 4, 5, 6, 7, 8 and 9. Here we are having 9 electron and 1 vacancy. It is represented as 1 hole is there. 1 hole is there. Here 1 electron plus 9 holes. 9 holes means 9 vacancies are there. So the spectrum is just reversed as in the case we seen earlier. So the ground state term become 2E, that is doubly degenerate E, and the excitation from on hole taken place from the ground state to the excited state. Here in the case of tetrahedral D1 and D9 systems, we are observing just reversed diagrams as we seen earlier in the case of D1, D9 octahedral. In the case of D1 tetrahedral compounds, the transition from 2E to T2, that is the G term is missing. G term means the gerade, the symmetry, the center of symmetry is missing. And in the case of tetrahedral compounds, the del T value is reduced by 4 by 9 del 0. That is del O means the octahedral crystal field splitting energy. And we can also say that the ligand field strength also is represented in terms of del 0 or del T, uh, and unit is dq. dq means difference in quanta. In the case of Cu plus 2x4, the copper is in plus 2 oxidation state, that is D9 system, and the tetrahedral ligand is attached to a central metal ion. We are getting a transition from T2 to E. Here also the G term is missing. The missing of center of symmetry. In the case of D4 and D6, we are expecting the same as here. The D1 and D6 having the 5 electron difference, and D9 and D4 having the difference in 5 electrons. According to the Orgel diagram, we can see that difference in 5 electrons having the same Orgel diagram. So for octahedral D4 complex, 1, 2, 3, 4, D4 complex, we are getting a transition from E energy level to T T2G. And for octahedral D6 system, 5 and 6 electron is there. The term is D. The term is D, and the multiplicity is equal to 5. Here the only change in the spin multiplicity. In the earlier case, the spin multiplicity is 2. In the case of D6 and D4, the multiplicity is equal to 5, and the transition is from T2G to EG energy level. Here is the combined Orgel diagram for D1, D6, D4 and D9. In the case of D2, D7, D3 and D8 orbitals, here we are having 2 electrons, and we get the total angular momentum value is equal to 3. It is denoted by the symbol F. There also a P term is also there having the same multiplicity, that is 3. So two terms are there. So we are getting a transition from T1G to T2G and T1G2 and T1G and T1G to 32G. We are expecting the three transitions, and there is a spin crossover is also there. Spin crossover is also there in the case of D2 system. The typical example is vanadium hexaco vanadium 3 plus complex. So the vanadium 2 plus ion in free ion having the ground state term 3F, and 3p term is also there. So we are getting the transition T1G to 3T2G here. 31D2, 3T2G, and because of the spin crossover, the energy of 3p and 3p state, that is 31G and A2G having the same energy. So we are getting only two transition in the case of weak field ligand. While the ligand field strength is increases by replacing a weak field ligand, that is water with ammonia. The splitting is more, so we get clear three excitations. That is, the three transitions are from 3T1G to 3T2G and 3T1G to 3T1G and 3T1G to 3T2G. For DA system, the example is nickel 2 plus system. Nickel 2 plus system. The dotted line represents the nickel ammonia complex, hexa ammonia nickel 2 plus complex, and the solid line shows the aqueous complex. The color is green and blue. We can see that the two spectrums having the three transition because there is no spin crossover in T8. 1, 2, 3, 4, 5, 6, 7, 8. The spin multiplicity is equal to 3. And we are having the combined diagram of D2, D7, D3 and D8. The crossover is happen only for D2 and D7 octahedral and D3, D8 tetrahedral. In the case of tetrahedral, the G term is not indicated. Here we are having another example for D3 electronic system, that is chromium 3 plus electronic state. Here the ligand field strength is increasing from left to right, and we can see that for fluorine we are getting the three transitions, that is the transition from A2G to T1G and to the T1G last to the T1G of P. In the case of oxalate and ethylene diamine and cyanide complexes, we are getting only two transitions because the difference is more high, so the excitation energy falls into IR region. So we are not getting in the UV visible range. So we are getting only two transitions. Here the spectrum of D5. In the case of D5, D5 octahedral Orgel diagram is equal to D5 tetrahedral. And the transition is, the lowest energy transition is from 6A1G to 4T1G. Here also 6A1G to 4T1G. The lowest energy transition is common in tetrahedral and octahedral because the ground state term is 6A1G. All the transition is spin forbidden. That is, the delta S value is not equal to 0. The G and U not used in the tetrahedral compounds. The spin state never crossover but repel each other. Having the same spin multiplicity, so they repel each other. In summary, in Orgel diagram, we are having D1 and D9 opposite together and D1 and D6 having the same. Likewise, the D1 and D4 having opposite interaction and D4 and D9 having the same. This is one type of example, one type of Orgel diagram. The second type of Orgel diagram having the relation D2, D3, D7 and D8. In this case, the second case, we are having D8 and D2 having the opposite. D2 octahedral just reverse of D8 octahedral and D7 octahedral just reverse of D3. D3 and D8 having the same type of Orgel diagram and D7 and D8 having the same type of Orgel diagram. Thank you.